Okay, looks like we got a few folks to start out. I guess I'll go ahead and start kicking off here for today's lecture. Oops, what did I just do? I hit a button I didn't want to. There we go. Okay, so today we're going to transition from the ordinal data context we were talking about to looking at how we go about modeling another type of categorical data, namely count data. Here, bring this up. There we go. And let's put a little more content in here. Okay, so count data. And so we're talking about things like counting up the number of times an event occurs within a specified time interval is the typical type of count we're talking about. As I said, that's another type of categorical or discrete random variable that we're working with. But unlike things like ordinal data, it does not have a fixed upper bound. Actually, I should contrast it also with binomial data. In either case, those things do have upper bounds, whereas in count data, theoretically, there is no upper bound to the number of occurrences within a given time interval. Another thing we'll be thinking about as we go along is that event counts can be viewed as what I termed here observed manifestations of what's called the underlying hazard for event occurrence. And for now, I'm going to start with just a fairly heuristic view of what hazard is, and we'll be talking about it in more detail when we get to modeling time to event data. But we can say that hazard is, loosely speaking, the instantaneous probability density for the occurrence of an event. Or another way of looking at it is it's the expected instantaneous event rate. Is another way of viewing what a hazard is. So again, we'll cover that in more detail when we get to time to event data, where we have to work very explicitly with hazard functions. But we'll also see that there's a close relationship between the modeling approaches we use for time to event data and what we use for modeling counts. They're both founded on this underlying notion of a hazard. And we can count data in a lot of situations in pharmacodynamics. This is just a very short list of some different possibilities here with some citations here for cases where PD models have been developed to describe counts of events. For example, in Cox et al. Here they described vomiting rates. In that particular paper, they modeled it primarily as a repeated time to event data, but a subcomponent of their description there actually involves modeling the counts over certain intervals. Seizures, there's actually been a number of articles out there describing models for seizure counts. This is one here by Raymond Miller et al. You'll also, there's some recent work that's been done by I'm going to forget the list of folks. Lavielle and I'm going to forget the other major investigator on it off the top of my head. But they've also developed some interesting models there for dealing with seizure counts. In that particular one, it's sort of beyond the scope of what we're going to talk about in this section, but we might be able to get on to that towards the end of the course. But it's one where there's an underlying what they term a hidden Markov model to try and account for a type of autocorrelation or serial correlation that occurs. There's urinary incontinence events described by in this Gupta et al. Article here, and neonatal apneic events described by C.J. Godfrey in this paper. So anyway, these are just a few examples of things that might be described by counts. And if I'm sure if you think about it, you can come up with other kinds of things. For example, you could imagine that if you were observing adverse events. In fact, many of these things fall under the heading of adverse events, but you could imagine counting up the occurrences of an adverse event rather than simply reporting whether or not they occur, and modeling the counts of those adverse events, for example. Okay, well, there's how do I want to put well, let me just sort of describe this. What I'm going to describe is what I've termed here the Poisson model. And it turns out that if certain conditions are true regarding the way events occur, then there's a nice theorem that says that the counts of those events can be described by a Poisson distribution, and that's what I'm describing here. So I term this the standard constant hazard model, and we'll talk in a little bit about what happens if it's not constant. But first of all, we'll describe the Poisson process, and the conditions we're going to talk about here. That would be, one is constant hazard, and that's basically says that the probability of an event within any very short time interval is approximately proportional to the length of that interval, and that essentially translates into the notion of constant hazard. Another condition is independence, and that's that the number of events in any two disjoint intervals are independent, and that the events are discrete. In other words, you can't have more than one event occur at the same instant in time, that you can only have one event at a time. If those three conditions hold, it turns out that you can describe the counts according to a Poisson distribution, and that's the statement right here, really, then, is that if those conditions hold, then the number of events in any time interval, which I'm calling here ti minus 1 to ti, the number of counts is a random variable, and it's distributed according to the relationship shown here. Here I'm using n to represent the cumulative number of events from time 0 to time t, so that when you take this difference, n of t minus 1, that's just sort of a fancy way of writing the number of events that occur during the interval between ti minus 1 and t. So anyway, the number of events, the probability that that number of events equals some particular value, n, just equals what you see on the right-hand side here. So you've got 1 over n factorial times the product of this hazard, that's what this h is, times the duration of the time interval, raised to the power n, times an exponential term where it's e to the minus the hazard times the duration of the interval, which is nothing more than a description of the Poisson distribution, and that's what I'm saying down here, where with a parameter equal to the hazard times the duration of the interval. And so you've got, so that's all this is really saying then, that the number of events is distributed Poisson. And having that relationship means that usually the Poisson distribution is the place we're going to start when trying to construct likelihood functions to describe these events, or the number of those events. And a little bit on some properties of the Poisson distribution. So here I'm just writing out, let's say, suppose that we've got some random variable x and it's distributed Poisson with some parameter lambda. Of course, x can take on the values going from, actually this statement isn't right. I need to change that. That should be x equals 0 to infinity. So it should be 0, 1, 2, and so on. So that can be so 0 to infinity. In particular, it has to be non-negative. The probability function then is described as you see here, so that's just a statement of what the probability function is for the Poisson distribution. Just 1 over x factorial lambda the x e to the minus lambda. And one thing we see is that the expected value for the x for our counts, it just equals lambda. In fact, that's usually the way we think about the model, Poisson model, is that we think of lambda then as being our mean number of counts. But in addition, it turns out that the variance of x is also lambda. And in fact, it turns out that's an important property that we will want to consider when looking at our data to assess whether or not the standard Poisson model is applicable. More on that shortly. Okay, so again, lambda we usually think of as being our mean number of counts. Another property that sometimes comes in handy is the one shown here that says if the random variables xi, where I can be 1 up to some number n here, if they're independent and each one of them is Poisson distributed with possibly different mean counts here, that's why it's lambda subscript I. Well, it turns out that the sum of those counts, basically, so you can total up the counts, and the total counts then is also Poisson distributed, but where the mean count for that is simply the sum of all of those average counts. An example where that can come in handy is when you're working with working in the context of a meta-analysis where perhaps all you have is summary data from some study where the quantity being measured is some event count. Then you can, and often what you'll get then is maybe they'll report an average event count over all the individuals in a given treatment arm. Well, if you take that event count and multiply it by, or that average event count, multiply it by the number of individuals in that treatment arm, well, that number is nothing more than the sum of the event counts for all of those individuals. And that sum then, if in fact the individual event counts were Poisson distributed, then that sum would also be Poisson distributed, and that could form the basis then of a model that you would use for meta-analysis of that type of data. Okay, so that's some of the core principles. What I want to do next then is let's go ahead and apply the Poisson distribution in the context of some data, and that's what we're going to do next. And in fact, maybe I'll step back here. What I'm going to be doing is actually using information from this Miller et al. Paper. I don't have the actual data, but I took their model and simulated some phony data here so that we could apply a model to that. So that's how the data you're looking at is constructed. Okay, so in our example, it's going to be a hypothetical case of, or semi-hypothetical, I guess, of the effect of pregabalin on seizure frequency. Again, it's simulated data based upon the Miller et al. Article, and they had multiple models in there, and this is the one they called their Model 3. It involved, it was dose response, so we've got, 5 different doses here, 0, 50, 150, 300, and 600. There were 100 patients per dose arm, 4-week baseline phase, during which they also get count measurements, and a 12-week double-blind phase, and the data will consist of the number of seizures in each 4-week period. So we've got a baseline period plus 3 post-treatment periods then that we're going to be measuring the seizure counts in each individual. So we've got multiple observations in each individual. So logically, we would want to account for within individual correlation of those values, again, or equivalently inter-individual variability. So we're going to do that in the model. Here's a representation of the data. Orient you to this, then what we're looking at are sort of empirical distributions of our seizure counts broken up by dose and time. So on the left-hand axis, these are histograms really, giving number of patients corresponding to each number of counts, and on the x-axis the number of accounts per 4-week period. As we go from bottom to top in the panels, we're going over time. So the bottom panels are that baseline 4-week period. Second panel is 0 to 4 weeks. Next panel is 48 weeks, and the top one is 8 to 12 weeks. And then as we go from left to right, we're going up in dose from our 0 dose, our placebo treatment, up to a 600 milligram per day dose. And then you can see the histograms here, if you like. Not really. I guess technically, I guess I'd think of this more as as a bar chart, really. So for each possible number of seizure counts here, you have a bar or possibly a bar. If it's 0, you don't see a bar, of course, in here. So you can get some idea of how many seizures are reported, and you can also get, roughly you might be able to look at it and get some idea of whether or not the drug seems to be favorably influencing that count. And to help that, I've overlaid on each panel the mean count on here, so you'll see that near the top. In fact, you can see, for instance, if we look up here at the latest time, if we go from the lowest dose to the highest, we do see a general downward trend in the seizure count, going from roughly 20 down to 14, and similar sorts of patterns as we go down until, of course, we get to the placebo treatment on the bottom panels, where it stays pretty much constant as we go across. I've also overlaid on here the variance of the numbers of counts across the individuals here for each one of these panels. One thing you'll see immediately is the variances in general are not only larger than the mean count, but substantially larger than the mean. One of the things that's telling us is that a sort of trivial use of the Poisson distribution, if we sort of did this as a naive pooled analysis where we just applied a Poisson distribution with the same mean count for every individual, it's certainly not going to be applicable because there is such a big difference between the mean and the variance. And that's further accentuated by what I've done is I've overplotted on here on each one of these panels a Poisson distribution with the same mean as the observed data, and you can see that that distribution does not do a very good job of describing any of the data that you see in any of the panels here. So again, a sort of a naive application of the Poisson distribution won't work here. However, well, more on that in a minute. Next plot here is just to give you more visualization of the dose-response relationship here. So I'm looking at mean number of seizures per 4 weeks. Each panel is a different period, so we've got our baseline period, our 0 to 4 week, 4 to 8, 8 to 12 shown here. And you can see that in general there, when you get to the post-baseline, there is a general downward trend in the seizure counts here. And so let's take a look at a model. In fact, this is really a Bayesian implementation of one of the models reported in the Miller et al. Paper. And what we're looking at then is our data here then is going to be the number of seizures in a 4-week period experienced by the jth subject in the ith period. That's what our subscripts are referring to there. So you can see I've written that as n sub seizure ij. That's going to be Poisson distributed in here. And where am I going here? Okay, that's going to be Poisson distributed. And our lambda j is going to be described here. So we've got some parameter called base here with some random effect. Here it's exponentiated, so it'll remain positive since lambda is an average count level, so it has to be non-negative. That would be for our baseline period here, thus the word base. And for the post-baseline period, we've also got possible placebo and drug effects in here. Our anticipation is that, if anything, those would tend to bring the count level down, thus the reason for writing it as base times 1 minus the placebo and drug effects here. Again, it's multiplied by the same random effect as it would be for the placebo case. The drug effect is just a good old-fashioned Emax model here in terms of dose. E placebo is just a constant, so it's just a parameter in and of itself. And our random effect here is just going to be a simple normal, normally distributed random effect centered about 0. And so that's going to be the model we're going to apply. Now, one of the things that, again, we're going to talk a little bit more about this in a moment, but by introducing this random effect on the average count quantity here, our average count parameter, that will actually induce that greater variance for well, a greater variance in the counts than the mean. So that sort of takes care of the problem that would have been caused if we had tried to use a naive model where there were no differences amongst individuals in terms of that average count. I'm just going to use weakly informative priors, but in addition I'm going to use a little trick to constrain these parameters so that we don't end up with a negative average count. And to do that, all I need to do then is make sure that this quantity here, well, first of all, I'm going to constrain base to be non-negative. And then I'll also constrain this term 1 minus E placebo minus E drug to be non-negative. And so if I do that, one trick for doing that is to restrict Emax plus E placebo to be less than 1, and to constrain E placebo also to be less than 1, because if there's no drug present in our placebo group, you need to also have that hold. And the trick for that I've chosen here is to reparameterize things. So I've defined 2 new parameters, one that I called P1 here, and another typo, that should be P2 right over here. So both of them I'm going to constrain to be non-negative by using log normal distributions for their prior. And then E placebo and E max are defined indirectly from those. Particular E placebo will be 1 minus P1, and E max will be P1 minus P2. And I'll leave it to you if you want to play around with that to convince yourself that we in fact achieve the desired constraint in here, so that we never end up with a negative value for our lambda term over here. And then finally, I've got weakly informative priors for everything else here. We've got log normal for ED50 for our baseline, and then a fairly broad uniform here for our inter-individual variation on our lambda term. Let's see, do I want to look at that here? Let's see, maybe it's even easier to look at it. Let me open it up in here. So let's open up 255. There we go. You actually have this in, you should have this in your course materials too. I'm going to open this count example here, .txt. Switch that over and make it a bit bigger. Okay, so in fact, let's see if we can make this, I don't know, I'll try and switch back and forth without making it too annoying here. So the first thing we're going to do is we have to describe our likelihood here. Our N seizure here is distributed Poisson, and that's what's going on right here in this line. So first of all, this is inside of a loop that goes over our observations, where this N obs is defined in our data set. Similarly, the end seizure values are also defined in the data set. So that's the number of seizures for a given individual, for our ith individual here. And that's going to be distributed Poisson with some mean here, lambda I. And then the next step then is going to be to essentially represent what you see here for our lambda j. And that's what's going on in right here. Okay, so we can see I've got base times our random effect term here. And recall again, we've got the basic trick of in our data set, we'll have a patient identifier, in this case called patient, which will be an integer from 1 to however many patients we have. And I'm going to, so I use an indexed, I'm sorry, and what was I going to say, a nested index here to grab the appropriate eta value. So that's our random effect, and that eta value is generated up in another loop where we loop over the individuals. And so you can see that in our loop here where we've got eta I, again, is normal, 0, and some precision, which we'll define down in the priors. Okay, so we've got our Poisson there. We've got our, so our lambda here, sorry, we're finishing up this with our lambda. So we've got our random effect in there, and then we've got in here our 1 minus, this term down here is essentially what you saw as 1 minus E drug minus E placebo, just written it a little bit differently and included a term here to take care of the fact I only want this to apply to the base for the non-base, this part of it to apply to the non-baseline. So that's playing the role of this bracket here with this thing breaking out between baseline period or post-baseline. So that's the way I use the equals function. So when time equals 0, equals time comma 0 is going to be 1, and 1 minus 1 will make it 0, and that'll wipe out the term over here. But at any post-baseline periods, this will be 0. So this then just becomes that 1 minus, and I put it all within quantity terms, so it ends up being 1 minus the sum of E drug and E placebo. E placebo again is just a parameter by itself, but E drug here I've got subscripted I because it's going to depend upon the ith dose, or the dose in the ith individual, and so that's finally defined in another equation here. So that's just our Emax model then. So that's our core model then. We've got our likelihood, which includes our inter-individual random effects, and then we come down to our priors. And again, I've defined this P1 and P2 in here as a set of parameters that enforces the constraint that we want our E placebo and our Emax plus E placebo to be both be less than 1. So that's what's going on right there. And then the rest of them are pretty straight ahead. I've got the log of ED50 is normal, and then I convert it back to the ED50 for later calculations. Similar thing for the baseline value, and our omega being the standard deviation for inter-individual variability, and converting it to a precision. And then the only other elements in here then are getting some terms in here to get some posterior predictions, so we can use it for some presentation and diagnostic purposes. So you can see up here, this would give us our individual predictions, again predicting a new observation in the same individuals right here. So again, it's identical to the likelihood other than the name on the left hand side. And then down here we take care of the calculations need to do a population prediction, where we essentially have to repeat almost all of our calculations. At least we have to repeat any that depend upon the random effects for the individuals. So you can see this depends upon eta pred, which in turn is generated up in this loop over patients. So we'll get our individual and our population predictions. Yeah, let's see. Let's see, I got a question here. Can I explain one more time how equals works in the model script? Yeah, equals is you think of equals as a WinBUGS function that takes two arguments. So you can think of it as equals x comma y. If x equals y, then it returns the value 0. I'm sorry, I said that backwards. If they're equals, it returns the value 1. And if they are unequal, it returns the value 0. Okay. And by the way, a reminder that anytime you forget any of those, just go ahead and pull up the help. Go ahead and pull up the help document for WinBUGS and go looking for the definitions of what they call logical nodes, where they describe the functions in there, and that also gives a description of it. Okay, so let's see, we got that. What else did I want to do? We're going to do, I guess, just move right on to the, well, quick look at the R script, I guess. Okay, again, R script, a lot of it's the same. This is called count example, thus that's the model name in here. Let's see, I don't think there's anything novel up on top. It's reading in the data set. We should probably pull that up so you can see it. Come on, open up. There we go. Okay, we got data sets. Pretty straight ahead. We've got a patient identifier here. The time, in this case, it's the time for the end of the interval over which the counts were measured, and in each case, the observation period was 4 weeks. We have the dose. Well, you can ignore the hazard. That was actually just thrown in there when I was doing the simulations. And seizure count. So pretend hazard isn't there. They think of so it's really just the 4 columns of interest: patient, time, dose, and seizure count. So you can see the various counts in here. You can also see that you have quite a range. And in fact, this was true in that you see is you have patients with very different characteristics in terms of typical numbers of seizures. So here you can see an example for patient 1. The seizure counts are relatively low. In here, in fact, in this case, the baseline was actually less than on treatment. Same thing's true for 2 is also low all the way through. You can start seeing 3 is getting a little higher. Then if we scroll down to take an example here of, here's an example of a patient with a very extreme occurrences, they're practically status epilepticus here in terms of extreme counts. So there's a very broad range of counts here, and it's one of the reasons, of course, why you do need to model the inter-individual variability here in order to make sense of the data. Okay, so that's our data that we're pulling up. There's some exploratory plots that this is doing, and I think they're all identical to the ones I showed you already. Let me double check. Yeah, that's just another way of viewing essentially what we saw already, so I won't worry about those. So let's skip over the exploratory plots. Frankly, they were mainly there for me to do the slides. Oops, just went too far. No, I didn't. I didn't go far enough. Okay, the bugs data statement, there's essentially no real data management to be done here. So you can see it just pulls out and gets the number of observations by counting up the number of rows in the data set. Number of patients it gets by counting up the number of unique patient values. In this case, it assumed that the patient identifier was already in the form of an integer that goes from 1 to n patients here. We've got our time, our dose, and our seizure count. So everything's pretty straight ahead there. Some initial estimates, and I'll be honest, I don't even remember where I dreamed those up. I might have even cheated and used the same values that were in the that were used for the simulation, but it's been a while since I did it, so I don't remember. But you could come up with some plausible values by essentially eyeballing the counts that you've got there to get some handle on most of these values. And then throwing some random variation about those to come up with different initial estimates for the different chains. We're going to want to grab all of our parameters here: base, E placebo, Emax, ED50, omega, and so on, as well as getting our posterior predictions. Ran this, actually the first time I ran this, and the version I believe you have, it only had 10,000 iterations per chain rather than the 50,000 you see here, and I'll show you why in a minute. And in fact, 50,000 is probably not even quite optimal here, but I'll show you in a minute why. Let's see, is there anything interesting going on down here that isn't more than the typical probably not. There's maybe a few interesting things going on in terms of some of the posterior prediction plots, and it's probably better to show you the plots than try to go through the plotting program. Let's go back to our data set. Anyway, let me show you what I've got here called count example old is the one using 10,000. Let's make it big enough to see. Oh, let's use PDF here. I'll just grab the first few. Okay, this is the history plots using 10,000 iterations per chain. And though some of the parameters don't look too bad, you can see that at least a couple of them could be better. Base, you can see where we've definitely got a wiggly snake thing going on here, and to a somewhat lesser extent that's also true for the ED50 in this. So you've got a pretty good hint here that even though the three chains are kind of intertwined, and so it's not suggesting a really gross convergence problem, we almost certainly don't have enough to have good precision for any inferences about that baseline parameter in here. So that's an issue that I see in that. I think we'll probably see, what do we got over here? Actually, surprisingly enough, the Gelman-Rubin-Brooks plot doesn't look that bad. In fact, I'm surprised it doesn't look worse, given what we see there. But I would certainly suggest more. And then if we look at the let me go ahead and pull up here. If we look at the our effective n values here, you can see though things like omega looks great, and Emax is probably tolerable even if not optimal. Same thing for E placebo. When we look at this base here, we've got an effective n count of only about 55, which certainly won't give us very good precision for that quantity. So if we wanted to make inferences based upon the baseline value, we don't really have sufficient samples to do that. Now it depends on how much precision we want. Now what I won't say what I did. If looking at this, we felt that maybe, let's say 1,000, an effective n of around 1,000 is really what we're looking for in order for our inferences. Well, then I would look at that and say, okay, well, it's roughly 50. If I do 20 times as many iterations, that'll take me to 1,000, and that would be at least a rough ballpark idea of what it might take to get that much precision for that parameter. So that's one way of thinking about this. Now, I didn't get quite that carried away. I just did a run with 50,000. Let me go ahead and bring that up. That's the run that was done using the R script I just showed you. Let's bring up the corresponding thing here, and you can see actually we get pretty much what we might have expected. Recall it was we had an effective N of, what was it? It was like 54 with the 10,000 iterations. Well, I did 5 times as many, and now I've got an effective N of a little better than 250, which is about what I would have guessed. Again, is that really enough? It depends in part on how important the baseline parameter is to your inferences in here. It probably gives pretty tolerable precision for the central tendency for our posterior mean. If you're going to be asking questions that have to do with looking at the tail probabilities, you probably want to do more. Let's take a look at the plots related to this. Okay, let's get rid of the old one here. Come on, get bigger. There we go. Okay, so again, this was done now using 50,000 iterations per chain, 3 chains, and what did I do? I think I tossed out 10,000 at the beginning for burn-in. And here you can see that generally we're looking better. You can still see some wiggly snake things going on with the base there, and thus, you know, you still might want to consider doing more. You know, at least on the order of around 4 times more than we have here to really make it more reasonable. There might be some reparameterizations that could make it more efficient too, but I haven't tried exploring that for this case. Okay, but everything else looks pretty clean in here. You can get your posterior, your marginal posterior distributions here for the various parameters. Again, things look pretty clean on the Gelman-Rubin-Brooks plots. You can look through here and get some idea of what our individual predictions are looking like. Here's for a this is for the placebo arm here, and these are a bunch of individual plots, so you can see some of the various trends you see with individuals in terms of their event counts. You know, got a bunch of them here. There's what, I think it was 100 patients per arm, so, and I've got what, 25 per page here, so there's 4 pages per arm. So you can get some idea looking across these. Let's scroll down to maybe one of the higher doses so you can see the trend over time a little better. And you can see some of that going on here. So done that. Here's individual predictions in terms of looking at the mean number of seizures as a function of dose for the different time points in here. What's this? This is just no, this is mislabeled. This should be time down here. This is just looking at the same data as we saw here, but turning around and plotting it against time. Let's see. This is looking at the variance. Recall the issue there that the variances were considerably larger than the mean. Thus, the reason why we couldn't use a naive pooled use of the Poisson distribution. But here we're showing that as we hope, including a random effect, was sufficient to also capture the variances. So this is looking at, again, the variance of the number of seizures versus dose and comparing the model predicted and the observed values. Again, these are in terms of individual predictions. This is another way of viewing the data, and what I've done here, actually this probably makes more sense to look at this in the population predictions, but I'll orient you to it while we're here. So this is, I'm looking at the number of patients against the number of seizures. So what you're really looking at then is sort of an empirical distribution of the event counts. And again, each panel you can see is for a specific time dose combination in here. And you can see that the dots represent the observed number of patients that report a given number of counts, and then the curves in here represent the posterior median and 90% credible interval for those event counts, or for the fraction of number of patients that report that number of event counts in here. Again, you can see that in general we seem to have captured that fairly well. Let's see, I think when we go to the next page, we're basically, yeah, we're getting it. Now we're looking at this as population predictions. So now we're looking at the posterior predictions of what might happen if you were to do essentially the same study in a new group of patients in here. So generally our prediction intervals are a bit wider. Again, here you're looking at the dose responses, and it seems to again have captured that quite well. So with our population predictions, things are still looking pretty good, albeit more uncertain because of the uncertainty in our in model parameters, as well as the inter-individual variation. Again, the variance is captured, and again the same plot here, but again you'll see broader intervals because of the it also includes the inter-individual variation as part of it. Okay. Trying to think of anything else other stories I wanted to tell on that example. Let's see, Andreas, what are you asking? Okay. Let's see. Okay, you're saying you'd like to share a trick with me to get the doses in the right order in this arrangement of panels. Use XY plot, N patients, seizures, format dose. Okay, I've never used format. Why, have I got them in the wrong order in one of these things? That's possible. Because the other thing is there's a... these are in the right order. Yeah, I'd be curious to know, do I have one of these in the wrong way? Let's see, that way I get doses 0, 4, 12. Oh, I do have this one in the wrong order. Okay. Yeah, that's one. That could be one way. Wasn't familiar with the format. The other thing that you can use is there are. Now I'm going to forget the exact name of the function, but I often use a function inside the GData collection, which is I think it's just called reorder.factor, which is a particularly nice one for doing that. But yeah, I didn't catch I had made that. Didn't have it treated as numeric in this instance. Yeah, and by the way, that just to point out that that's actually the times in this case, but the point is still applicable here. It's treated it as a character string in effect here, which is not the way I wanted it. Yeah, good catch on that one. I'll have to take a look at format. I wasn't aware of that one. As I say, I usually use a GData function to get the ordering right. Okay, I think, well, I guess I didn't actually look at the model parameter estimates. This is just looking at those and trying to think if there were any stories I wanted to tell around it in particular. None that jump at me right now. And let's see, I had the same plots. Okay. Okay, before I move on to the next bit about counts here, I guess let's see if there's any other questions or comments. I'll just keep my eye open for them in case somebody's still typing out there. Let me go ahead and start working towards the next topic here. Now, one question that comes up is, we were starting out with presenting the Poisson model in terms of a constant hazard. What do we do if we have a time-varying hazard? Which, in the case of working with counts, this is also referred to as a non-homogeneous Poisson process. Or is that non-homogeneous? I don't know. So it turns out that the Poisson model can be extended to those cases where the hazard varies systematically with time. Again, that's known as the non-homogeneous Poisson process. And if the hazard, again our sort of expected event rate, is a function of time, then the number of events in any time interval, again I'll use the ti minus 1 to ti, that turns out to be a random variable distributed according to the relationship you see here, where instead of, before, recall, we had a term here that would have been like our h for our constant hazard times the interval of time. Well, now instead I've got h as a function, but I'm integrating it from ti minus 1 to ti. And I do the same thing for the one in the numerator here. And I want to say that I missed a negative sign. Sorry, let me flip back just to check. Yes, I did. Unless I turned the endpoints of the interval around. Let me check. Yeah, there should be a negative sign right there. Okay. So said another way then is that when we have a time-varying hazard, we can say that the event count over an interval is Poisson distributed still, but where we have to consider taking the integral of our time-varying hazard over that interval from ti minus 1 to ti. And in fact, if in cases where all of your observations are always occurring over the same time interval, looking across a bunch of individuals, it's actually not even possible to distinguish whether or not the underlying process is homogeneous or not. Looking at that, the only way you can really tell is if you do have observations taken over different time intervals and are able to detect that there's some systematic changes over those different time intervals. In the absence of that, the distinction is really not identifiable. But it does point out that the basic concept of using a Poisson model is still applicable in those cases. It's just that you may have to, if you are going to be working with different either durations of time or different intervals in some sense, whether they're at different times overall or of different lengths, you would actually need to try and identify what that underlying hazard function is. What we deal with a lot when we're working with count data is the problem of what is commonly called overdispersion, and in some cases we'll also be working with something termed zero inflation. So let me talk through that a bit. So recall then, for a simple Poisson random variable, the mean and the variances are equal. But now let's suppose that your data consist of event counts over the same length of time for a group of patients. So basically what I'm going to do here is try and construct sort of the simplest case that leads to overdispersion. So let's start with that. So we've got our event counts over the same length of time for a group of patients, much like the example we did. And if the expected event count is the same for all of the patients, then the data would be distributed according to a common Poisson distribution. And in that case, the sample mean and the variance will be approximately equal. But what if each individual's event count is a sample from a Poisson distribution, but the expected event count varies among the individuals? Well, in general, then, the sample variation will be greater than the sample mean, and the data are not consistent with a common Poisson distribution. And when that happens, we call that overdispersion. In other words, the event counts then are more dispersed than would be expected based upon the standard Poisson model. But it turns out there are a number of ways in which we can extend the Poisson model to account for that sort of overdispersion. And in particular, the most common ways you'll see for dealing with that are something that we could term continuous mixture models, in which the hazard itself is randomly distributed. And we're going to look at a couple of such continuous mixture models for doing that. Now, another situation that can occur is, suppose that you have a group of patients and they're actually drawn from two different populations, but you're not necessarily able to a priori identify which population they're from. But in particular, they come from two populations where one of those populations has an expected event count of 0. Well, that too is actually going to result in a sample variance that exceeds the sample mean, but it's doing so for a very different reason than the overdispersion category I had just discussed. In this case, we're talking about a situation where there's going to be an excess of zeros compared to Poisson distributed data. And in this case, what we can do is we can extend the Poisson model by using a discrete mixture of a Poisson model plus a simple categorical model for the probability of no events. So that's what we're talking about right here. And that is often termed a ZIP model, which is an acronym then for zero inflated Poisson. So that's the other situation that can lead again to a sort of a category of overdispersion. But it's probably better to distinguish between those two categories. What we're actually going to do is, rather than go through a whole example sort of as a lecture issue here, what I'm going to do is incorporate an exploration of these different kinds of models as part of your hands-on problem 4. So what I'm going to do next here is actually step through the directions sort of for hands-on problem 4, and then leave you guys to work on it, and then we'll go over it on Thursday. Okay, so our hands-on problem 4 is going to be looking at count data. We've got our patients in our phase 2 dose finding study recorded a number of efficacy and safety related outcomes in a daily diary, and those events included an indication of whether or not they experienced excessive coughing. And what we're going to model here is going to be the total number of coughing events in each patient as a function of dose. And we're going to focus on exploring some different event count models. And that sort of gives us also a good setting for a bit of learning about applying some model evaluation and selection in the context of a Bayesian analysis of some odd type data. Okay, so remind you what our phase 2 dose finding trial looks like. So we've got our phase 2 dose finding trial in cystic fibrosis patients. This is actually the same one we were looking at it back in problem 1. It's a parallel design, 100 patients per arm, multiple arms of our MI2, and so we've got our placebo 20, 40, and 60 milligrams per day given over 24 weeks. Our adverse event measurement here is going to be the number of coughing events, and in this case we're not going to look at a longitudinal model here. We're just going to total up all the coughing events for each individual over the entire 24-week period, so we don't have longitudinal data to work with. And we're going to construct a model for the count of coughing events as a function of dose. Our data set here you'll see is called MI2 cough count data. .csv. Let's open that up real quick here. It's our hands on 4. And where to go here? Oops, just did something I didn't want to do. Come on, close up. There it is. Okay. Okay, so the data is just going to be, again, we've got our patient identifier, dose, our cough count. Well, this has time, but in this case they're all 24. That's kind of ignorable. It's really only the first 3 columns we're going to work with here. So we're just going to work with a very simple set of data here in this case. Let's go full screen here. Actually, that's not quite what I wanted to do. There we go. Okay, so just to give you some views on the data here. Here we're looking at number of patients versus our counts of cough reports for each patient in here. So you can see we've got a lot of patients here that have 0 counts, especially down here at the 0 dose. Again, these are the panels correspond to the different dose levels, 0, 20, 40, and 60 milligrams per day. And you can see, especially down here at the lowest, we actually have nearly half the patients are reporting no cough in here, and then it drops off fairly quick. But then as we go up here, we do seem to see some increase in cough incidence up here, and you can see I've overlaid the means here as well as the variances. And though not as extreme as the seizure count case we're looking at, we do see in general then that the variance is larger than the mean going here, with the variance being a bit more than twice the mean in all of these. Again, I've overlaid a Poisson distribution that has a mean equal to the sample mean. Again, you can see it's kind of shifted, the peak is shifted to the right compared to the data. And anyway, so we've got some indication of overdispersion just looking at the sample statistics here. On the right, I've given you something to visualize dose response. We're looking at our mean count versus dose, and you can see it's going up in a roughly linear fashion in here. So we're going to propose some competing models for dealing with this. The first one is sort of our most naive approach, which is going to be to use a simple Poisson model. So where you're just going to have the number of coughs in the individual is going to be Poisson. Actually, I probably could have just put a lambda I here. I put it as lambda I times t. When I've written it this way, the lambda I you can think of as representing our sort of our average event rate, or it's really our hazard function in here, times ti, but ti in this case is 24 weeks for all the individuals. If we did have dropouts, that would make more sense perhaps to include the ti here. So it doesn't hurt here. It depends on how we want to interpret what we're looking at. And the lambda I here just depends upon dose. There's no random effect, and it's just a linear function of dose. In here, we've got and just weekly informative priors for A and B. Then we're going to look at some competing models which are intended to account for the possible overdispersion or zero inflation. And first, let's take a look at what is probably the most commonly used model to try and deal with overdispersion, and that's the negative binomial model. And we're going to write it actually in terms of an alternative way of viewing the model. As it turns out that a Poisson gamma mixture model is exactly equivalent to a negative binomial, and that's the easiest way to implement it in WinBUGS in particular. But it also is it provides a fairly convenient parameterization and interpretation for us. But we could have, if you go looking up the negative binomial distribution, it too has a fairly easy to write distribution function. And in fact, if I was doing this in something like non-mem, I'd probably write the negative binomial distribution directly. But again, it's more convenient to write it as the Poisson gamma mixture in the case of WinBUGs. So the way we're going to write it here is that our main likelihood for cough is going to, for a cough count here, is going to be again Poisson, lambda I ti, but where lambda I is going to be gamma distributed. And again, that combination, if you have Poisson where lambda is gamma distributed, that is equivalent to a negative binomial distribution. And there's different ways that we could then parameterize this. Now the gamma is parameterized in two parameters here, alpha and beta. One property of the gamma distribution is that the mean of this quantity is going to be the ratio of alpha over beta, the first parameter over the second, and the variance is going to be, what is it, alpha over beta squared, as I recall. And so what we're going to do is we're going to make it gamma alpha beta I, where beta I is going to be alpha over lambda I. And if you work that out, you'll see then that the mean of this then will equal this lambda I hat. So that's what lambda I hat is intended to represent as our mean, which we'll describe then as a linear function of dose. Now when I do this, this sets it up in such a way then that the standard deviation is proportional to the mean. So if you go through and calculate the standard deviation for this entire quantity, that's the way it'll work out, is that the standard deviation will be then proportional to our lambda I hat. There's other ways we could have parameterized this, where maybe alpha is the thing that depended on I instead of beta, that would create a different relationship with the mean. And in fact, you might even want to do a model comparison based upon some of those alternatives. But this is usually a fairly reasonable choice. We've got, again, weakly informative priors for our three parameters, because in the end, given with all this hoopla, there's actually only three parameters in the end. There's just A, B, and alpha. Everything else is derived from those. And this was just pointing out, oh, this is actually, I forgot I'd had this on the bottom. This is just pointing out then that it's parameterized again so that our expected cough is going to be our lambda I hat times T, and the variance is going to be lambda I hat times T over alpha. Again, and that's just emphasizing that the standard deviation is proportional to the mean. Okay, so anyway, that's probably going to be our prime candidate then for a model to take care of the overdispersion. But there's, even though the negative binomial is very commonly used, there's nothing sacrosanct about that as being the one to choose. One could imagine a variety of other mixtures where this distribution here could be something else. You want it to be non-negative, but beyond that, it could be pretty much any other probability distribution in here. In this case, you want it to be a continuous distribution. And one reasonable alternative would be to use a Poisson log normal mixture. And if you look at this, what you'll see then is that I'm doing essentially the same thing I did with the Poisson gamma, except that for our lambda here, I'm going to make it log normally distributed. So again, the log then of lambda I is going to be normal with some mean, in this case log of lambda I hat, and some variance sigma squared. Again, this is a situation that will result again in a case where the standard deviation, actually let's double check something. Yeah, again, where the standard deviation is proportional to the mean, just like it was for that Poisson gamma case, but with a somewhat different shape distribution in here. And again, it's a 3-parameter model, and I've used weakly informative parameters or priors for all of these. Okay, so that was 3. So we've got 3 cases, so far. One for our standard Poisson, and then we've got two competing models that will cause a certain degree, that will be consistent with the overdispersion we saw. Let's take a look at a third case, and that's the zero inflated Poisson model. And so again, this is going to be one where it's a mixture really of two models. It's going to be a mixture of a standard Poisson plus just a simple discrete probability for having a count of 0. So we're going to I'll just term this zip here. So I'm just going that our n cough here, our number of coughs, is going to be distributed according to our zip model, where we've got one set of parameters at lambda iti, and then this probability pi, which is, let's see, I guess the way I wrote this is the pi is going to be the probability of it being part of the standard Poisson. And I've written this out this way. By the way, I've written it in a way that makes it consistent with the way we'll implement it in WinBUGS. So you've got the first term, which is you've got 1 minus pi. So this is the probability that the observation it comes from that distribution, which says it's always 0. And I've written this actually in terms of a Poisson with a mean of 0. That's actually kind of a WinBUGS trick in this case, because the Poisson distribution with a mean of 0 is really a is a degenerative case, because that says that the probability that the count is 0 is always 0. So again, but that's a useful trick in terms of implementing it in WinBUGS. And then we have plus pi times our standard Poisson model, where we just x times lambda. Actually, to be consistent with the other things, I just realized these should be lambda iti over here. In fact, it should be. So there should be a ti there, and ditto right there. Okay, and this is just writing that out in another form here. So that says that in the case when x is equal to 0, then the probability for that is going to be 1 minus pi times pi, or plus pi. And it's because this p Poisson 0 and so on is actually just a 1 in this case. And then alternatively, when x is greater than 0, it comes from you get the Poisson probability multiplied by pi, and our lambda I hat in this case. Actually, do I want lambda I hat? I do not want a hat. Sorry, you got too many typos on this slide. Lambda I is just going to be our simple linear model. So we have, again, it's another 3-parameter model, where now our third parameter is going to be the probability that the observation comes from the standard Poisson distribution. And I think, yeah, that's actually as far as I'm going to take it with you. This is now your mission then is to implement these 4 models and to compare the results. So at this point, I recommend you take a look at, certainly you want to take a look at how well they do in terms of graphical comparisons, looking at posterior predictions and how they're able to capture the results. The other thing you may want to look at is some quantitative comparisons, looking at things like the expected deviance. One of the things you can get from WinBUGS, as well as the R to WinBUGS, is an estimate of what's called the deviance information criteria, which plays a role similar to something like the Bayesian information criteria or Keiki's information criteria for comparing models. So I'm going to make that your mission at this point. So I guess I'll see if there's any last questions then before I let you go. Okay, nothing I see popping up yet here. I'll keep my eye open for another few minutes here, but in the meantime, I guess I'll say goodbye until I talk to you again on Thursday, and we'll go over the results of the different count models that were being proposed for this example. See you then.